Chapter 2, Motion in One Dimension. Motion is a change in an object's position in time. And in order to compare the motion, we always have to have a frame of reference. So our frame of reference is going to be where motion begins. And what I want you to do is I want you to conceptualize and picture where motion begins being like the origin of a graph. So if I say something is going to the right, I'm going to call it positive. If it's left, I'm going to call it negative. If it's up, it's going to be positive, and it's down, it's going to be negative. But remember, what's my starting point? Where the motion begins. So again, that sign convention that we use in math class, that's called the standard Cartesian sign convention, and that's what we're going to do in this class. Now, there's some Greek symbols we're going to be learning throughout the year, and one of the most important one is the one that looks like a triangle, and that's called delta. And delta means change in. So delta is always the final minus the initial. So if I said delta t, that's actually TF minus TI, the final time minus the initial time. Now, most of the time in physics, when we're going to learn equations, usually it has to do with an elapsed time. So it might say over a 2-second interval. So delta t would be the interval. Right now, we're going to learn two important things. First, we're going to learn distance and displacement. Every quantity that we ever learn in physics, when I introduce it, you notice in little parentheses, when I give you the definition, I'm going to tell you it's either a scalar quantity or I'm going to tell you it's a vector quantity. So a scalar quantity just means that it has a number and a unit. That's what scalar quantity means, number and unit. So distance, we'll call distance actually, we'll call this d instead of x, and the unit for it is meters, because we use meters in the metric system, and it's just a number and a unit. So distance is straight line movement from the starting point. Now displacement is a change in position. So this symbol is x, and this is a vector quantity. So a vector quantity has a number, a unit, but then it also has a direction. Okay? So that's the difference. So an example of distance would be 10 meters. An example of a displacement would be 10 meters north, because that has a direction. But the best way for you to really understand something is to conceptualize it. So let me show you a couple of examples. So let's say we're playing baseball. Does anyone in here play baseball? Okay. So let's say you're at the field, here's home plate, and you hit the ball, and you're trying to run to first base to beat it out to get a single. Okay? So you're running as fast as you can. Now, what's the distance from home plate to first base? 90 feet. But you're running as fast as you can, so you run to first base, and you run past first base about 10 feet, and then you turn around and you come back and you stand on first base. Okay? So everyone can picture that now in their mind, right? The distance that you travel is going to be 90 plus 10 more, so your distance is 110 feet. Now your displacement is from where you start to where you end up. So I started at home plate and I ended up at first base, so my displacement is equal to 90 feet. So that's the difference between distance and displacement. Okay? But we need to do a couple of examples. One example is not sufficient. Okay? So let's say I go for a walk. So let's do another example. And this is where I start off. And I decide to walk 5 meters this way. So I walk 5 meters this way. Then I walk 7 meters this way. And then I walk 2 meters this way. Now my distance is going to be 5 plus 7 plus 2. So that's going to be 12. And 2, this is going to be 14. But my displacement is where I start to where I end up, and this is my displacement, which is not the same. Okay? So that's our second example. Let's do one more example. Does anyone in here on the track team? How far is it around the track? Okay, so here's the track, and it's 400 meters around the track. So let's say you go out, and normally it would be a perfect oval. I didn't draw it perfect. And you run around the track 2 times. So the distance that you travel, you go around the track 2 times, so your distance is going to be 800 meters. But again, I go around the track twice. 1, 2, so my displacement is going to be equal to 0. Why is it 0? Because I'm back where I started. Whenever we learn something, it helps to have conceptual examples, because most of us are visual learners. I'm a visual learner. If I see it, it helps it. If someone talks about it. So these are just different visuals or conceptual examples to help you understand the difference between distance and displacement. Okay. All right, so now we're going to talk about some other stuff. We're going to talk about speed and velocity. So speed, and I'm going to call this S, and the reason I didn't originally change it is because of your textbook. But so speed is distance per unit time. Again, this is a scalar quantity. So if I was going to give an example, I would say, okay, I'm walking at 10 meters per second. That's a speed. Now, once I get up to velocity, velocity is displacement per unit time. So this would be 10 meters per second north. This now has a direction. If I wanted to calculate the average velocity, it's going to be the change in displacement or the change in time. So again, delta is the final minus the initial, and then this is the change in time, but most of the time they'll give us an elapsed time. So let's look at an example. It says a bicycle rider travels 22 kilometers in 3.2 hours. What is the average speed of the bicycle rider? So I'm given the distance, I'm given the time, and I want to find the average speed. Now, whenever we work problems in this class, and we're going to do it tonight in our homework, we're always going to write our given. We're going to write our find. We want to find speed. And the reason I'm doing is some books, they use, I think your book uses the same variable for both, and it makes it confusing, so we'll just do it a little bit different so you understand speed and velocity, distance and displacement. So it says a bicycle rider travels 22 kilometers. So D is equal to 22 kilometers in 3.25 hours. What is the average speed? So we want to find F. So first we're going to write our basic equation, and then we're going to substitute our values. Whatever mathematical number we do to the number, whatever we do the numbers, we do the unit. So if I divide 22 by 3.25, I do the same thing to the unit. So a kilometer divided by an hour is a kilometer per hour, which is the correct unit for speed. Now, instantaneous velocity means at one particular instant in time. Okay? So as we go on and we look at graphical analysis, we'll see that that's just for one particular instant. And it makes a difference if something's moving at a constant speed or if something's accelerating. Now, we're going to do graphing another day. So we're going to skip past the graphing notes because I decided to do all the graphing in one day. It makes it easier. And we're going to go to acceleration. So acceleration is the rate of change of velocity. Acceleration is also a vector quantity. So it has, again, a number, a unit, and a direction. That's what vector means. So this would be, the unit is meters per second squared. So this would be 10 meter per second squared down would be an example of an acceleration. So here's an example. It says, now we have a bunch of equations for acceleration. Now some of them we're going to do today, and let me jump ahead to the next page. So here are all the equations we have to memorize in this chapter. This is the way they appear in the textbook. So it says delta x is equal to 1/2 vi plus vf times t. Delta x is equal to v delta x. This makes it really, really, really difficult to memorize with all these deltas in here and all this other stuff. So this is the way that I remember the equations. So you see, while I'm trying to remember them, you see how I took the deltas out? Does everyone see that? But if you just know in the back of your mind, I know the delta's there, so if they give me a time interval, I know this t is actually the time interval. Okay? Equation has an x, and this one has a v and a t. So how do we know which equation to use for which situation? We know which equation to use for each situation based on what we're given and what we find. And that's why it's important to write all that out when we're doing our homework. Okay? What we're going to do is, if we write our given and our find, the problem pretty much solves itself. Then what we're going to do is we're going to carry our units out to check our work. So let's look here. Here's an example. And it says a car moving on a straight level road changes speed from. So if you look at this, the key word there is from. From tells us that's how it's starting off. So then I know that this 35 is going to be my initial velocity. Then it says 2. So that 2 tells me that this is going to be my final velocity. Then it says in 5 seconds. So the 5 seconds is actually the time interval, so I'm going to say t is 5 seconds. Find the acceleration. So then what I'm going to do is I'm going to say, what are my 4 variables? I have vi, I have vt, and I want a variables. So the basic equation is actually vf is equal to vi plus at, but since I want to solve for a, I'm going to rearrange the equation to solve for the unknown in terms of the known. So what that means is I'll subtract vi from both sides, so vf minus vi is equal to at. Then I'm going to divide both sides by t, so I have vf minus vi over t is equal to a. So then I write my unknown in terms of my known, I substitute in my values, and I solve. So 45 minus 35 is 10. Now, whatever I do to my number, I do to my units. You see, I say 10 divided by 5 is 2, right? But now, what is a meter per second divided by a second? Well, remember when you learned about fractions and you learned that if I want to divide fractions, it's the same as multiplying times the reciprocal? So I say a meter per second times 1 over a second is a meter per second squared. Is that my correct unit for acceleration? Yes, it is. One of the great things about physics is you have a foolproof way to check your work every single time by carrying your units through, so you'll never make a mistake. So that's what I wrote here. So carrying your units through to check your work catches algebra mistakes. So what do? To solve the problems, what you're going to do is you're going to write your given, you're going to write your find. This is going to help you identify the 4 variables, and then you'll know what you need to do. Now, in the rest of the notes, I did examples for every single type of problem. But what I'm going to do now is we're going to work all the homework problems together because it's better to work them together to understand them. So that's what we're going to do right now.